In the previous video, we started discussing differential equations, and we have found a complete set of solutions to the second-order linear homogeneous differential equation with constant coefficients. And in this video, we'll say more about the initial value problem and discuss some methods to approach the inhomogeneous case. So for a differential equation, which is in our case a y double prime plus by prime plus cy is equal to 0, given some starting time t0 and constants y0 and y0 prime, we want to find a function y of t such that the differential equation is satisfied. So y of t0 is equal to this constant y0, and the value of the derivative y prime of t0 is equal to y0 prime. So there's a theorem that for an ordinary linear constant coefficient homogeneous second order differential equation, so the equation that satisfies properties on the previous slide, the initial value problem has a unique solution. So to put it differently, the following map is an isomorphism. So the space of solutions of this ODE into R2, which sends y into the vector y of t0, y prime of t0, is an isomorphism. It is a one-to-one correspondence. So the existence of the solution asserts that this map is surjective, right? So there's always a, for every point in R2, like there's a pre-image. So there is always a solution with specified value and first derivative. And the uniqueness component asserts that it is injective, that is, there is at most one such solution. So this statement, this theorem, is very can be formulated very neatly in terms of linear algebra. So we won't prove uniqueness in this class. It will be proven in a more specific class on differential equations, but we can give you some ideas of why this can be true. For now, let's just take it as a given. So in the previous video, we saw that there was always a two-dimensional space of solutions to a differential equation of this form. And we have an injective linear map between two-dimensional vector spaces, and therefore there is an isomorphism. So that takes care of the existence part. Now let's talk about the solution. So solving the initial value problem in practice uses the same ideas as the above argument. So if you have the equation y prime prime plus y is equal to 0, so in the previous video we learned that, or you probably guessed it, that this cosine and sine have the basis of space of solutions, right? This equation appears a lot in physics, in theory of oscillations. And to solve the initial value problem or finding a solution which has y of 0 is equal to 3 and y prime of 0 is equal to 4. So the general solution has this form, a cosine t plus b sine t. And once you determine the values of a and b for which y of 0 is equal to 3 and y prime of 0 is equal to 4. So we can compute 3 is equal to y of 0 is equal to a times cosine 0 plus b sine 0. It's equal to big A, right? Because sine, when you plug in 0, sine vanishes and cosine is equal to 1. And then, so when you compute the derivative, you have this function here, negative a times sine t plus b times cosine t. And then when you evaluate it at 0, you get b, and b should be equal to 4. So this is the initial value problem solution, 3 cosine t plus 4 sine t. In general, the last step may involve more complicated linear algebra. So suppose instead we wanted a solution with y of 1 is equal to 1 and y prime of 1 is equal to 2. Right, so then neither sine nor cosine vanish at those points. So we have the system of equations two linear equations for A and B, right? So the which we can write in the usual form, right? So the matrix cosine 1, sine 1, negative sine 1, cosine 1, acting on the column vector AB is equal to 1, 2. Okay, we know how to solve it, right? In fact, we should be able to write the solution almost immediately. So the matrix is clearly invertible, right? It's very easy to compute the inverse. So the answer is given by this formula. So the so A is equal to cosine 1 minus 2 sine 1 times cosine t plus this constant sine 1 plus 2 cosine 1 times sine t. Okay, now let's talk about inhomogeneous equations. We'll try to solve the equations of the form a y double prime plus by prime plus cy of t is equal to f of t with some pre-given function f in the right-hand side. Let's rewrite this equation as the differential operator a d2 over dt squared plus b d over dt plus c acting on y of t is equal to f of t. So we know that this is a linear equation, just like the matrix equations that we talked about in the first part of the course. Recall that the ax equals b equation could be solved if and only if b was in the range of a. So moreover, solving this equation was the same as taking the given spanning set for the range, namely the columns of A, and finding a way to write B as a linear combinations of these columns. In the finite dimensional case, we had sitting in front of us a spanning set for this range. So in this present infinite dimensional case, because space of functions is infinite dimensional, we do not have such a basis. But any such would be infinite. So in a systematic treatment, we would try to understand the range of this linear transformation. But that would involve some infinite dimensional linear algebra in a serious way, which is beyond the scope of this class. But it is doable. So it is totally doable. But instead, we can just feed some and sort of somewhat arbitrary functions into this linear transformation. Right? We could just test it on some given functions and thereby learn some elements of the range. So, and then whenever we want to try and solve the full differential equation, we'll ask whether the right-hand side, the function f of t in question, is in the span of those elements of the range that we have found. So let's do the first order case for the inhomogeneous equations. So say we have we want to study the range of this operator d over dt minus r. So we'll do it by just computing d over dt minus r acting on f of x for various functions. The most natural set of functions is polynomials. So if we act with this operator on constant function 1, we get negative r. If we act on t, we get 1 minus rt. And then acting on t squared, we get 2t minus rt squared. Acting on t cubed, we get 3t squared minus rt cubed, and so on, right? So, so we see that all polynomials are in the range, right? So we get one polynomial, acting on one polynomial, we get another polynomial, right? So in fact, you can see here that when r is not equal to 0, then the range is just the set of Pn itself. And then when r is equal to 0, you drop the degree by 1, right? Because it's simply the derivative. Now, let's look at an example. Solve this first order differential equation, y prime plus y is equal to t squared. So we know that t squared is contained in d over dt plus 1 acting on space of polynomials of degree at most 2. And in order to find the elements which map to it, it's now a linear algebra problem. Right, so we would solve it by, for instance, choosing a basis in P2 and writing this operator as a matrix. And we know how to do it. Right, so let's take a vector in P2, this polynomial at squared plus bt plus c, act on it with a d over dt plus 1. So that's the result of this action, right? A times 2t plus t squared plus b times 1 plus t plus c. And then we impose the condition that this polynomial is equal to t squared, from where we can solve it for these 3 unknown coefficients a, b, and c. Well, and sort of it's called the method of undetermined coefficients. So essentially you are guessing those coefficients by suggesting your differential equation a certain form of the answer, or the ansatz as it's called. Well, or it's, you know, same kind of thing that we do in linear algebra all the time. So you can check that, well, it's kind of, you don't need to, yeah, you can just check that a equals 1, b equals -2, and c equals 2, provide you the solution. Sort of they make sure that this statement is satisfied. So the polynomial is equal to t squared. And then the solution of the ODE is t squared minus 2t plus t. Now let's try an exponential function. So we remember we're looking at the space of various space of functions on which the differential operator acts. So if you act with this operator d over dt minus r on e to the st, so it will get s minus r times e to the st. So this function is in the range, provided that s and r are different numbers. Now let's try a polynomial times an exponential function, or sometimes it's called quasi-exponential. So this is what we had before, and now if you act with this operator on t exponential, after some simple algebra, we get again an exponential plus the polynomial times the exponential. And then you take t squared as a polynomial in front of the exponential. Again, after some algebra, you get 2 terms, right? So this one, 2t e to the st, and t squared e to the st. And so on. You can see that everything stays in range, right? So the image of this operator on the acting on these polynomials multiplied by the exponentials stays in the same space, right? You get polynomials of degree at most, in this case 3, and in this case 2. So polynomials times the exponential is in range. And yeah, so like all the set of, so Pn times the exponential, which is the polynomials of degree up to n, multiplied by the exponential, we have a similar action as before. So this is the range is Pn times the exponential when r is not equal to s, and it's Pn minus 1 when r is equal times the exponential when r is equal to s. So we just decrease the degree by 1. Now, and in fact, you know, using the calculus rules, the derivative d over dt minus r acting on the product of f times the exponential, well, is equal to f prime t times e to the rt plus f t r e to the rt, right? And then minus f of t r to the rt. So see here that the if this r here, if s is equal to r, right? So then we make sure that the last two terms get canceled. So you just get exponential times the derivative of the function in front of it. Just a helpful fact to remember. Example, you see here there's a 3 here and 3 there. So solve the equation y prime minus 3y is equal to t e to the 3t. Well, so we know that this t e to the 3t is in the image of p2 of e to the 3t. So remember, when we take a derivative, we lower down the degree of the polynomial by 1. So we should try a general element in this case. So take the quadratic polynomial multiplied by the exponential with coefficients a, b, and c, and act on it with the differential operator, d over dt minus 3, acting on this polynomial. And then because of the fact from the previous slide, right, it's very easy to compute the answer, right? So for example, the contribution from the last term completely disappears, right? And from here you get just 2a, and here you get b from the differentiation. So in order for this to be satisfied, a has to be equal to half and b is equal to 0, and the solution is well, a solution, one of the solutions is t squared over 2 times the exponential. Okay, now let's look at second order equations. So we return now to the second order case, the inhomogeneous case. So there is a non-trivial right-hand side. And we studied the range of the operator, the differential operator of the second order, given by this formula. So let's talk about how to factor it. So let r plus and minus be the roots of the equation ax squared plus bx plus c is equal to 0. And then you can formally factor out this quadratic polynomial in differential d over dt as such. Right, so you can sort of verify it by expanding the parentheses here and dealing with d over dt as a variable and also as a differential operator. So it's just d over dt times d over dt is equal to the d over dt squared. It's the second derivative that this equation is satisfied. Right, now what can we do with it? So each of the above items are some. So this is a linear algebra transformation of the kind we considered before, right? And this is a linear transformations of the same type, right? It's a transformation on the space of, well, differentiable enough functions to itself. And we are asserting that the composition of the two on the right is the one on the left. So notice that we could swap the order here, right? So in this case, those two components, they commute with each other. So there's no difference in writing in picking the order. So from the previous story, d over dt minus r acting on Pn gives you this action. And then if you do it twice, right, you have more choices, right? Because you have to basically apply this result twice. So acting with the second order operator on the space of quasi-exponentials, right, polynomials multiplied by exponentials, you can get Pn times e to the st if s is different from both roots, right, if all three numbers are distinct. And then you lose 1 degree if s coincides with one of them, right? And if you lose 2 degrees if all three are the same, right? So it's easy to if you need to convince yourself in the validity of this fact, just pick some example or several examples and check that it works. Some simple quadratic polynomial which is easily factorizable with the real roots. Now, yeah, so and then if you go back to what we have started, so the action of the second order differential operator on the space of functions gives you this, where r plus and minus are the roots of the polynomial ax squared plus bx plus c. Let's do an example. Take differential equation y prime prime minus 4y prime plus 4 is equal to e to the 2t. And then, so luckily here, this polynomial is easily factorizable. So it has a double root 2. So we write it as a is an operator d over dt minus 2 squared on y of t is equal to e to the 2t. So we know that this function is in the image of p2 e to the 2t from the previous slide. So we should try and see like to substitute the general element in this space. So take a quadratic polynomial with arbitrary coefficients a, b, c, at squared plus bt plus c times the exponential, act on it with the differential operator d over dt minus 2 squared, right? And then because of the rule that we discussed before, right? If this coefficient here is equal to this coefficient here in exponential, then differentiation is very easy, and then you just do the double derivative of this quadratic polynomial, which simply returns 2a. So the solution is given by 1/2 t squared e to the 2t. Okay, now let's consider a more interesting right-hand side. So it's a sum of two different exponentials, but with the same homogeneous part, with the same left-hand side. Observe that if we solve separately equations with the exponential with e to the t on the right and e to the 3t on the left, then we can add the solutions to get a solution of the equation above by linearity, right? So we should use the properties of linear algebra to our advantage. And in the context of differential equations, well, sort of inspired by physics, people call the linearity the superposition principle. Like, you know, in physics, in this linear approximation, you can add forces or probabilities of functions to each other with signs. Okay, so we just did the solution of this equation. It's the t squared half times e to the 2t. Now let's solve this one with the exponential to the 3t on the right hand side. Now 3 is not the root of auxiliary equation, so 3 is not equal to 2, right? So the s is not equal to neither r plus nor r minus. In this case, r plus and r minus are the same numbers. So we know that the so that exponential belongs to the d over dt minus 2 squared acting on p0 e to the 3t, right? So we try a general element of that space, which is just a constant. And the solution is given just by the exponential itself. So see, it's very easy. So once it's there's this mismatch, once it's not the same, then you lose 2 degrees. So finally, adding the formulae. So because of these two statements, which are true, so we find by superposition that this function here satisfies the equation.